Let's see some examples of LTI systems and analysis of them. Okay. So we'll go back to our RC circuit. So here we have an RC circuit, a resistor connected to a capacitor, and then there is an voltage source, and the input of the voltage source is some signal x of t. The output is the voltage observed across the capacitor, which we'll call as the output y of t, and we want to analyze this system. Okay. So how do we analyze this system? Of course, we'll write the Kirchhoff's voltage law, which means the voltage at the source is equal to the voltage across the individual devices that we have here. So the voltage across the capacitor is nothing but 1 by C integral of the current that is passing through this capacitor, right? So that's what we have written here. So at any given time instant, if you want to find out the voltage across the capacitor, how would you find out? It is the integral of the current that is passing through. So that's what we have here. So basically this is the Kirchhoff's voltage law. Now from this we want to characterize completely this system. So the system here is input x of t and output y of t. Now let's do some manipulation on top of this and then check first of all if this is an LTI system or not, and identify what happens to the system. Okay. So first what we are trying to do is we are trying to write the input-output equation relationship. Here we have an extra variable I of t, right? So we want to get rid of this and just have the input and output signals and nothing else. So we'll take the derivative on both sides. So to get rid of I of t, we can write that the output signal, when you take the derivative of that, you get I of t, and you replace that here, and you replace that here, what you get? So basically you substitute equation 2 in equation 1. You substitute equation 2 in equation 1, you get the input-output relationship that is given here. Now this is the system model that we want. So we have the input here, we have the output here. Now is this system LTI? So what do we mean by this? Is it a linear system? Let's check if it is linear. So for an input x1, let's say we get an output which is looking like this, y1, and for an input x2 you get something which looks like this. Now what if you feed in input x1 of t plus p times x2 of t? Okay. What are you supposed to get? Which is of this form. Which is exactly of the form that we want to say that this is linear, because this is 1 plus RC d by dt y1 of t plus the same expression here, 1 plus RC which is the output that we get here and here. So this entire expression is the output that we get here, and this entire expression is the output that we get here. So this satisfies linearity. So hence this system is linear. Now is this time invariant? Now what if you feed in x of t minus some capital T? So what happens? So when you feed in a signal which is time shifted, what happens to the output here? The output also gets time shifted here, right? Because this is not a function of time and this is a derivative. So you can say d by dt of t minus t is same as d by dt. The derivative does not change because of time shifting. So the input-output relationship does not change because of time shifting, and hence this is still time invariant. So this entire system turns out to be an LTI system. So which is great. So now we have an input-output relationship which is given to be an LTI system. So we can simplify the representation of this circuit, because we can write the input as the output plus RC times d by dt of y of t, which means I can say that the output y of t is nothing but the input subtracted with the scaled version of the derivative of the output. So, you can represent this entire system as input minus RC times the derivative of the output. So, this is a simple block diagram that we have here, which represents the input-output relationship in an RC circuit. Now, we can also represent this in an alternate way using an integrator. So, how do we do that? So, we can just integrate the equation here. So, if you integrate it, what would you get? You get integral of some x of tau d tau equals integral, so we can say minus integral y of tau d tau equal to RC of y of t, which means the output y of t is equal to 1 by RC of integral of x of tau minus y of tau d tau. So, you can take the output, subtract it with the input, integrate it, scale it with an RC, and you will still get the same output. So, both these systems are equal. So, we have a very simplified block diagram, and there are two different block diagrams. You can implement one of them with a derivative, you can implement the other with an integration. So, either you can have the derivative here at the output alone, or you can have the integrator here at the input, and both are equivalent. So, that is what we have here. So, we have a very simplified form. As long as you have any circuit which can eventually be represented by these equations, you can characterize them by a very simple block diagram like this. So, you can reduce and simplify circuits using these block diagram representations. You don't have to have complex RC circuits. So, this reduces or simplifies our analysis. How does this simplify? Let's see. So, once you have a block diagram like this, you can say that, okay, now I know that this is an LTI system, I can represent it like this. What would be the LTI system's characteristics? If we know the impulse response, we can completely understand the characteristics. We can completely understand the characteristics of the system. So, how to find the impulse response? In this case, we know that if we feed in an impulse, that is x of t is equal to delta of t, then the corresponding output is what we are looking for. So, if we can somehow find this output, then we are done. So, y of t corresponding to this del of t is what we want. So, that is nothing but the impulse response. We need to find h of t that satisfies this equation here. So, what are we saying here? We are saying that the derivative of h of t is in fact equal to delta of t minus h of t times 1 by r. So, this is what we are saying. So, if we can find the h of t that would satisfy this equation, then we are done. That is the impulse response that we are looking for. So, what does this equation tell us? It says that when you take the derivative, you are getting one part which is equal to the actual signal whose derivative we are computing. This is something that we have seen before. Remember when we said that the complex sinusoids are nothing but the eigenfunctions of derivatives and integrals. You pass a sinusoid or a complex exponential, and what happens at the output of the derivative or the integral operation? You get a scaled version of the input itself, the actual exponential signal itself. So, that is where the exponential signals, which are complex sinusoids, actually are going to help us. Now, we are seeing exactly something of that form here. We are taking the derivative and we are getting the input itself scaled with some quantity here. In other words, if we can assume that h of t is going to contain some exponential term, then we can get this component that we are looking for. Of course, it can also contain some other signal, okay, with some scaled constant. Let's say the constant is c. So, if you take the derivative of this signal, what do we get? We get a times e power at times cz of t plus e power at c times d by dt of z. Now this gives us exactly what we wanted, because what is that? That is this term. So this term is equal to a times h of t itself. Okay. If that is a times h of t, then from that we have already figured out what is a. So what is a? So a here, just compare this term and this term. Both are supposed to be equal, which means we have a to be equal to minus 1 by r. Okay. Alright. Now we have still another term left, and we know that this term must be equal to delta of t. This term must be equal to delta of t. What should have been the actual signal z of t? So we have a signal z of t whose derivative somehow is giving us delta of t. So which means we know that the signal that we are looking for is a step function, because the derivative of the step function is the delta function. So how do we find the signal z of t? So we have that e power at c times t by dt of u of t is equal to 1 by rc of delta of t. Now we know that t by dt of u of t is delta of t, and e power at times delta of t is equal to e power a times 0 times delta of t. This is a property of the delta function, which is equal to delta of t itself, because e power 0 is 1. So which means this entire expression here boils down to a very simple expression, which is equal to c times delta of t. Now this tells us what the value of c is. The value of c is 1 by rc. So now we have a very simple expression for the impulse response that we got out in a very simple manner, right? So this tells us the impulse response of the LTI system that we have here is nothing but 1 by rc e power minus t by rc times u of t. So this is the impulse response that we are looking for, and that completely characterizes this LTI system of the RC circuit. So the RC circuit is an LTI system, and we know its impulse response, which means for any arbitrary input signal x of t, we know that the output y of t is simply nothing but the convolution of the signal that we have here with the input. So this can tell us the output for any kind of voltage signal that you are applying. So let us say you are applying just an input which is an let's say step function, which is just turning on the voltage. So what would be the output in that case? So in that case the output would simply be minus infinity to infinity 1 by rc e power minus tau by rc u of tau convolved with u of t minus tau d tau. So what would be this expression? This will be 0 to infinity 1 by rc e power minus tau by rc u of t minus tau d tau. And u of t minus tau, when you plot it, how does it look like? So u of t minus tau is something of this form, where this is t, this is u of t minus tau. This is the time reversed version of the step function. Okay. So the entire integral is now non-zero only when tau is between 0 and t. So this now integration is between 0 and t. So simplifies this expression. So what happens to this integral? This is 1 by rc times e power minus tau by rc divided by minus 1 by rc t to 0. So this RC gets cancelled. So then we have e power minus 0 minus e power minus t by RC, which is equal to 1 minus. So this is the output of the RC circuit whenever you feed in an input of a step function. So what does this tell us? It tells us that if x of t is equal to a step function, then the y of t is nothing but something which is going to exist only when this t is greater than 0, which means that is also multiplied with step function. Look, because the limit is between only 0 to t, so this output is going to exist only between 0 to infinity. And at 0, here what do we get? T equal to 0, what do we have? At t is equal to 0, we have 1 minus e power minus 0, which is 0. So at t equal to 0, we have 0, and then as t increases, this value slowly increases, which means you have something which is increasing exponentially like this. But then of course, the maximum value it can reach is 1. So at t is equal to infinity, we have e power minus infinity, which is 0. So the maximum value here is 1. So this is what we have obtained as the output. Essentially what happens when you apply a step input voltage at the input of this RC circuit, the voltage across the capacitor slowly builds up, and at infinity equals to whatever is the voltage of the input that is applied. So this is the output that we see. So output is nothing but 1 minus e power minus t by RC. So all we had to do was just compute the impulse response, and from this impulse response we found out what would happen when you apply a DC voltage.